So if that's our LCD, now, Mike, what method were you using? Did you use the one we did in class, or did you find an LCD of everything and then multiply by the reciprocal? How did you?
I usually find the LCD and add the two numerators and put it all over in one fraction, and then I usually flip it around into multiplication.
So the other method, okay, that's fine. So I'll do that method then. So this is not the method we approached in class. We took two methods and we chose one kind of. So Mike went finding an LCD on each spot and then multiplying by the reciprocal, which is fine. It's actually probably the way I've done it more often than not. Okay, so let's take a look. If you solved it the other way, you could still do this, obviously. So in the numerator here, right, what do we recognize? If we want a common denominator up top, we'd have to put a u plus v, u plus v, u minus v, u minus v, u minus v, u minus v, u plus v, u plus v. There's also a lot of room for error with the letter u and v. Anybody realize that?
Yeah.
Just confusing me too. So be careful with that. The minute you have letters that look similar, what you usually do? Yeah, make them like X and Y if you want to, okay, or something else. So what we need to recognize is that we've got pretty much, looks like 16 FOIL examples here. No, 8 FOIL examples here. So all the denominators are the same, which is great. So the numerators here, what did you do, Mike? Did you distribute them out and then collect terms and stuff? Okay, that's the way I would approach this. So you're good until this point. So you're still good here. So let's continue. Let's rewrite this whole thing. So what do we notice is that the denominators are both the same, aren't they? The denominator of the overall numerator. So let me write this out. Okay, this denominator is u plus v, u minus v, for sure. This denominator is u plus v, u minus v, also for sure. Why do I know that? I know that because I'm looking at this example here. I see that the same factors. And what does this problem want me to do? What do you think I'm going to have to do next? What's the easy approach? Yeah, I'm going to FOIL out the top. Absolutely good. Okay, I'm going to FOIL out the top. So I'm going to have, if I FOIL these out right here, I'm going to get u squared plus 2uv plus v squared. Okay, that's what I get from this portion over here. Then I have to go to the other spot, and I'm going to have a big plus sign here. Again, u squared, but minus 2uv plus v squared. So I'm going to extend this fraction line a little bit so it fits. Again, this is all over this major fraction, which I'm going to kind of like just bold in here. That's the major fraction right there. And I'm going to do the same thing up top over here. What I recognize, though, is that this here clearly cancels with this right here. And we have like terms we can combine also. So we cancel this with this for sure. Now, I'm going to continue to multiply at the top, but what's the thing that I was trying to point out? I jumped in and said let's FOIL, so I didn't want to do that. But what do you recognize about this problem? What could you do to make it easier?
Cancel the volumes.
Yeah, that's exactly right. If you have the same denominator in both fractions, those denominators actually cancel. This denominator here cancels with this one right here, leaving you with just a simple fraction, whatever this is over whatever this is. Now, you can prove that true to yourself. Think about this. You're going to end up, you're dividing this whole thing, right? That's what this bolded in division sign is. So you're going to multiply by the reciprocal of this. So take this denominator, the whole denominator, the major denominator, flip it and multiply by the major numerator. Okay, so in your mind, flip this and you'd multiply it up here. Well, this would cancel with this when this is up in the numerator, up over here. They would cancel up here like that, cross cancel. So in the end, you can really cancel those also. We'll continue multiplying at the top, but let's show that we can do that. Okay? Again, you can do that because in a moment you're going to multiply by the reciprocal. Mike, in a second you multiply by the reciprocal. Did you see them canceling on those or not? Okay. So here, at this point, either you would do this, right, cancel it like this, or multiply by the reciprocal of this denominator. So let's keep going and we'll show both methods. So let's multiply at the top. Okay, multiplying this times this, we're going to get the same thing we got from this down here. So if we don't, if we did it once and it wasn't in our head, just copy it down. Minus the entire expression. Okay, now recognize that I put a minus and I put a bracket there because I'm subtracting that entire expression. So my squared terms on the top are going to cancel. You notice that? Because I'm subtracting u squared and I'm subtracting v squared. Then I'm subtracting the negative 2uv, which means I add to the other 2uv. Now, notice I canceled these, but if I didn't cancel them, let's say hypothetically I didn't cancel them, I would end up simplifying this numerator up here first. Okay, in simplifying this, u squared, negative u squared. V squared, negative v squared. Then I have 2uv minus negative 2uv, which is a positive 4uv. Actually, let me take this and move it down first. 4uv. And let's say I didn't cancel this denominator and this denominator instead. I left it. Now, I would take this fraction and multiply it by the reciprocal of this overall denominator. Now, this is u squared plus u squared is 2u squared. V squared plus v squared is 2v squared. So I've got 2u squared plus 2v squared. And I put that in the denominator down there because I'm taking the reciprocal of this. And I'll notice now that I can cross cancel. U plus v, u minus v. Okay, so my cross cancellation occurs. And as a result, I get 4uv over 2u squared plus 2v squared. Now, I can cancel, I can reduce it with a 2, I guess, on both. I think that's the only thing I can really do here, right? So let's take it down to a 2 in the numerator and get rid of the denominator. Okay, it's got to cancel out of both of those, obviously. So the factor of the GCF of 2, take out 2, that cancels with 2. Now, again, guys, notice something, and I'm going to point it out, so just look up, please. The portion here where we canceled this out with this would have left us with 4uv from here and 2u squared plus 2v squared from here. So 4uv, that was this, and 2u squared plus 2v squared was down here. So when this happens again next time, if you see this, just cancel them out. Okay? Again, these denominators cancel because you're really multiplying by the reciprocal, and they cross cancel in the end. Others use the other method, multiplying the LCD on the top and bottom. You don't have it in front of them in those. Just to check the answer, make sure it's right.
Are we going to have anything that's long?
Probably not like that long, no. That would be like, I mean, if you did that on your own without stopping to explain it, it'd probably take you at least 4 minutes, maybe 5 minutes. If you did it on your own, you know? I mean, like not talking about it at all. Probably not that long, but I mean, a problem or two of, of like we have to find a common denominator or multiply by the LCD in all terms. I think the other method is a lot quicker. Remember multiplying by the LCD on the top and bottom we did in class? That method's faster, I think, than this. That's why this one took a while, and I did stop a while talking. Yeah. But when you use the other method, things just cancel right away, and everything reduces. Makes it a little easier, I think. Other questions on the problem set? On the problem set. That's it? Okay. Let's review for the test for a little while. So let's start with Descartes' rule signs. Let's quickly review some of that stuff. So we had things we talked about in that section. 2 of them were Descartes' rule sign. 1 was the intermediate value theorem. And the other 2 theorems were the boundedness theorem, upper and lower bounds. Okay? So let's talk about those 5 things. That's pretty much what this section is going to be about. I'm going to ask you to remember the quiz you had? If you could do that quiz plus a problem using rational roots, you'll be fine. Not going to be able to use your calculator, but the problem will definitely be able to work out using the rational root theorem, using Descartes' rule signs. You can see how many positive roots there are, negative roots. So what I'm thinking is we do an actual problem from beginning to end, where we have to find all the roots of it using the 5 theorems. And you may not have to use them all. You may not use the intermediate value theorem, right? The remainder sign might not switch, so they may not occur. But understanding all those topics from the quiz, if you can do those problems, but also being able to do one big problem that contains all those problems would probably be the best way to study. So let's do an example of one of those, and I'll pull up a problem that works for us. Section 8.7. Okay, let's try this one, see how this works. So we've got x to the fourth, f of x equals x to the fourth plus x cubed minus 10x squared minus 4x plus 10. Start right away. List your possible rational roots. Start by listing your possible rational roots. What do we have for the possible rational roots here? P's over Q's. What's Q, first of all? Yeah, Q is the A value, the leading coefficient. So what is it in this case? It's 1, which makes this very easy, right? When you have P over Q, you have to look at all the combinations. But if Q is 1, then the denominator doesn't matter. So pretty much list the factors of P. Plus or minus 1, 2, 5, 10. Makes life very nice, right? Let's use Descartes' rule of signs looking at the original polynomial. How many sign changes do you see in this one? Ryan, how many sign changes do you see? 2. 1 there and 1 there. He's absolutely right. Okay? 2 sign changes. So what does that mean? If there are 2 sign changes in the original function, what does it mean? Charles?
At most 2 positive real roots.
Yeah, why at most, Charles? Can you explain to everybody? What does that mean?
Off by 2, so it could be 0.
Yeah, you could have 2 real roots, or you could have 0 real roots. Real positive roots, sorry. Real positive roots. Okay, so at most 2 positive real roots. Now, recognize this, ready? It does not mean those 2 roots will be rational. They could be irrational. The 2 positive real roots could be like 8 plus or minus radical 2. Those are both positive numbers, but they're both irrational. Okay, so this is just telling us that there's 2 positive real roots at most. So we might not get any positive roots when we test in the synthetic table, because the synthetic table tests the rational roots, p's over q's. Again, these are the possible rational roots. This is telling us that there's just 2 real roots. They could be imaginary, and they could be irrational. Okay? And we'll talk about imaginary when that comes up. And we have x to the fourth, so we know that we could have at least 4, or at most 4 roots. 2 of them could be imaginary, 2 could be irrational. 4 could be real. You could have 2 real, 2 imaginary. You could have 2 real, 2 irrational. You could have all 4 imaginary. You could have all 4 irrational. There's all these possibilities. But what do you notice is that they come in pairs when it's to the 4th degree there. Okay? You could also technically have, let's see if this is right. Yeah, you could have 2 rational roots, or 3 rational roots, and 1 irrational. The irrational roots don't have to come in pairs. They usually do, but they don't have to. But the imaginary roots have to come in pairs. All right, let's switch the signs, or let's take a look at f of negative x, so we can see at most how many negative real roots we'll have. And f of negative x, what's the one thing I want to do? It's very simple here. Look,
all the variables with odd exponents?
Yeah, all the exponents that are odd, like here and over here. So switch these signs pretty much. That's what putting f of negative x in does to something. And we see that we have 1 sign change, 2 sign changes still. All right, so we know that there's 2 of each at most, which is good to know, because when we test things in the synthetic table, if we had gotten an answer now, or say our answer said there were at most 4 positive real roots, and imagine we had no sign changes. It'd be great, wouldn't it? What would that do? If we got 0 sign changes when we tested f of negative x, what significance would that have? You could rule out all the negative roots. Right? If we got at most 0 negative real roots, we could have ruled out all the possible negative roots from up here. We could have only tested positive ones. Unfortunately, life doesn't always work out well. We got 2 and 2. So we have to try some of the roots. Now, try something like 1 or negative 1 first. Because if one of those turns into an upper or lower bound, you know which way to search, above or below. You pick like the middle, and you pick a number in the middle. If that doesn't work, you then search on the one side or the other. So pick a number like 1. 1 is the easiest number to test in a table anyway. Now, we're going to use the boundness theorem. Somebody's iPad? We're going to use the boundness theorem when we look at the signs in the synthetic table. When are we going to use the intermediate value theorem? When are we going to use the intermediate value theorem? Where does that come into play? This is the one that everybody kind of forgets about.
The remainder switch signs.
If the remainder switches signs, remember what that means?
There is a root somewhere between the two numbers that you tested.
Yeah, there's a root somewhere between the two numbers you tested. Because really, ready? A remainder of 5 means that the y value is 5. So here's the x-axis in the graph. I test the number 2. I get 5. That means that's the coordinate 2, 5. Then I test the number 3. Then I get negative 4. Well, how do I connect these points? I have to cross the x-axis. So there's got to be a real root between those two numbers you tested if the remainder sign changes. Yes? And you notice that happening? All right, so let's take a look. Don't give it away yet. I just want to try it first. Somebody read me the numbers. I'm going to write it down on here. What do you got for the coefficients?
1,
Go ahead.
1, -10, -4, and 10.
1, 1, -10, -4, and 10. Let's try 1 first. Notice, by the way, your book doesn't make a table this way. They do a table the other way. The reason I do it this way is because you can keep testing numbers afterward. So you just make rows. Okay, so extend this line down and keep testing more numbers if the first number you test doesn't work. Okay, so we got 1 times 1 is 1, plus 1 is 2. 1 times 2 is 2. 2 and -10 is -8. 1 times -8 is -8, plus -4 is -12. 1 times -12 is -12, and 10 is going to give me -2. So this is not a root, it's not an upper bound, it's not a lower bound, God bless you. It's not an upper bound because the signs are not all the same. If the signs were all the same, it would be an upper bound. If the number we tested, instead of being positive 1, were negative, and then the numbers in the table had alternated, it would be a lower bound. But this doesn't give us any information besides the fact that we're close to a root. Right? Look at the y value. It's -2. If this y value here, this remainder, is 0, we're at a root. So we're close to a root. So let's try a number near that. So we can either try 2 or -1. 2? All right. I'll go with 2. And again, you have no real way of guessing besides just taking a just random guess here. Simply because we're not using our calculator on this section here. So we want to try this without it and see how you can do with it. So we bring down the 1. Now, by the way, that's something I've noticed as a mistake some people make. For some odd reason, sometimes when you do the second row, they forget to bring down the first coefficient. Always bring down that 1. Okay, they'll carry over the number they're testing, and I've seen people start with a 2. Make sure to bring down that 1 right there. 2 times 1 is 2, plus 1 is 3. 6 and -10 is -4. -8, -4 is -12. -24 and 10 is going to be -14. So did that help us really? What did our graph do? Our graph just went from, right? From 1, -2 over to 2, -14. So the graph is still decreasing, isn't it? So I can visualize what's happening right now on the side. I can do that by plotting these points. 1, -2 is here. 2, -14 is down here. That's what's happening right now. So what should I do? Yeah, let's try a negative number and see what happens. Let's try -1. Okay, and again, I'm stopping to talk about this. You don't stop. You just keep going, right? Say, all right, you know what? Positives didn't work. The graph is dropping. Let me go the other direction. Let me go to -1. It should take you 20 seconds to go through each one of these rows. Come up with the answer. Go to the next one. Try it. Come up with the answer. Okay, nice and quick. So we get -1 and 3 is going to give us 2. -2 and -4 is -6. 6 and -12 is going to give us -6. It's going to be 6 and -14 is going to give us -8. So that didn't help us really. Wow, thanks, Mike. And then jump the gun went there. We got 0 there. We're going to have 0, -10 is -10. 10 and -4 is going to give us 6. And -6 and 10 is going to give us 4. Try which ones? 5 and -5.
Wait,
Well, what are you going to notice before we go any further? That's a good point, Niall. But it's not between, be careful. I see the sign change here, right? But there's something else going on here, right?
So this is you testing the negative number?
No, you test the negative numbers, right? But it's not this sign change that's important. You put that.
It's never ever between 1 and -1.
Between 1 and -1, really. Take a look. Isn't there a sign change between these two also? And aren't they closer in the graph? Let's graph this. Where's -1, 4? Graph it. It's right over here, right? There's -1, 4. So where is it going to cross the axis? You're right, it needs to be valued here. But between the numbers 1 and -1. Hey, be careful. You want to say, right? No, there you're getting at? With the 2 and the -1. And that's a good point you noticed at the switch. That's good that you picked up on that. But recognize that between 2 and -1, there is a root, yes. But we can be more specific with our search domain. We could say that there must be a root between -1 and 1. Okay, we can see that clearly here where we connect those two dots. Okay, so yes, that is absolutely right. Between 2 and -1, there's a root, but be more specific. Between 1 and -1, somewhere here, there's definitely a root there. Okay? Nina, what did you say to test?
5.
Okay. So let's bring down the 1. 5 times 1 is 5, and 1 is 6. 30 and -10 is 20. 100 and -4. Test 5. Are we getting an upper bound? Is that what we're going to get here? Okay, I'm just seeing we're going to get positives for both of these. So we get all positives down the road. So once you recognize that, the numbers can get bigger and bigger. Right? 5 times 20 is 100. 100 and -4 is 96. 5 times 96. Why would I want to do that math? First put positives. So this is an upper limit. Okay? Well, if that's an upper bound, what does that mean? What does that mean if there's an upper bound there? We should test numbers below it. Well, do we have any numbers below it? Do you have any numbers below it? We tried 1. We tried 2. We tried -5 and see what happens there. Okay, but at least we know that this is an upper bound. But we still have to go to the negative sign now. We've got no positive numbers above there. Now, what we can recognize is this. We should look at the graph of this and see that this is also intermediate value theorem. The graph of 5 and some huge number means it's up here somewhere, right? All the way from that top corner, way further up, right? A number like 5, 500, this graph would have to turn around. So let's start looking at the graph. This is what the graph would really look like of this. This might not be a minimum. It might continue down further and come back up, but it's got to cross back to get to that point. So we know that the graph's going to do something like this. So there's 2 of our roots. What kind of roots do you guess those roots are? What kind of roots are they? They're probably irrational roots. Because we tested all the rational roots in that range, and we didn't get any. So there's a good chance those are your irrational roots there. So we test -5. Read me your line. What do you got, Nina, for -5?
I got 1 and -4, 10, -54, 280.
And 280, which makes that a lower bound, right? Why do we know that's a lower bound? The signs are what? Yeah, alternating. And you're testing a negative. Remember, only when you're testing a negative and they're alternating is it a lower bound. Only when you're testing a positive and they're all the same, either all positive or all negative, is it an upper bound. You need to be testing a positive to test for upper bounds, a negative to test for lower bounds. Okay, so a positive number cannot be a lower bound. All right, this is unfortunate. The last number we have to test is really -2, because we know, and it doesn't work. Okay, so what do we conclude as a result for a problem like this? Honestly, what would you conclude? Are all 4 rational, actually? Did we plot these other numbers? This is going to be all the way down here. Let's see. -5 is all the way down here. So, yeah, this graph has to turn around again, it looks like. Yeah, it's got to come back around, so it's got to hit through here at some point. And then it must do this somewhere else. So it looks like all 4 roots are going to be irrational. Okay, we can know that because of this. At least we know at least 2 are irrational, and the other 2 at first I thought they could be irrational or they've been or imaginary. But because of the fact that this this negative 5 is such a negative number. Oh no, it's a positive number. Sorry, it's a positive number. So it might not loop around.
You have two irrational, two complex.
Yeah, you might have two complex conjugates or two imaginaries, the other ones. We don't know for sure though. We have to test the other numbers. So this is going to go on up here for a while because we're up at 280. But if we tested negative 10 or another number, I wonder if this graph would turn around and come back down. Let's see. Let me look at the graph of it on the computer. All four turn out to be irrational. All four turn out to be irrational. Okay. So, do you understand the process of what you're going through? What happens if you had gotten one of these that worked? That's the next question I have for you. So let's do a hypothetical. We make up a function that's really simple that will work. So let's say we've got the function, it's loading, hold on. X cubed plus 2x squared minus 5x minus 6. If I test the number like 2 in this one, I'm telling you 2 will work so we can see. And I test this. And we've all done this, right? We plug a 1 in, bring it down. 2 times 2 is 4. Here, we're going to get that. Minus 5 is 3. 6 is 0. What do I do with these values that I get as a result? Yeah, I write the depressed equation, right? I just want to remind ourselves so we all know this. What do I do with that depressed equation? Set it equal to? 0. And I want to find the roots of this one now, right? Now, this happens to be quadratic, so what could you easily do? Just factor or use the quadratic formula. What if this had been x cubed? What if we started with x to the 4th, and this had been x cubed? What would you do with those numbers? Yeah, you make a new table with those as your headers. Let's write this down so we're all clear, because a lot of you made this mistake on the last test. A lot. You make a new table now with 1, 4, and 3 as the headers, and you test new numbers. You test the other possible rational roots you listed from the P over Q list. So when you listed your list of possible rational roots, you probably listed 1, 2, 3, and 6, right? The original function. Positive or negative, 1, 2, 3, and 6. Well, 2 worked, so maybe you try 2 again, because 2 could be a double root. Now you could have a double root. So try 2 again, probably won't work. So then you try another one of the roots, but you have to try them in the next table. Again, if this had been cubic, write yourself a little note that says, if x cubed, new table. Okay, and that table has these new headers here, or whatever you would have had. I was trying to call that, bring that example up the last one, but unfortunately there were no rational roots in that example. Any questions on this?
There's no rational roots, like, what do we do for our answer? Just like
I'll say find all the possible rational roots. If not possible, give as much evidence or give as much detail about the roots as possible. Okay, so you might say, oh, there's 2 irrational roots because I saw the intermediate value theorem occurred twice. The other 2 roots could be complex or they could be irrational. That last example, they happen to all be irrational. But if you had said 2 are irrational, 2 are complex based on the work you had done, that would have been fine. Okay? Once you test all the possible rational roots that are inside the bounded interval to test using your upper and lower bound, which was 5 to negative 5, we tested all those roots. We can't do anything more really. Okay, don't sit there and try points forever. All right, let's take a look at 5-6 real quick. So it's about just adding or subtracting rational expressions. Okay, so let's say we had an example of the following. X plus 4 over x squared minus 2x plus, or let's say, plus, no, let's say minus instead here. Minus 15. And then we'll say minus, on this side, x plus 1, x squared, minus 4x, minus 5. to subtract these two expressions, what do I have to have first in order to do this? An LCD. Okay? Now this is the one time that you're finding an LCD and using it. You're not multiplying through by the LCD or anything like that. Okay? It's not an equation. We're not worried about that. So it's just an expression. So it's not an equation. So go ahead. How would you find an LCD? What's the easiest way to start? Yeah. What do you get?
For the first one, you get x minus 5, x plus 3, second one is x.
And recognize the common factor in both. That's probably going to happen if you're going to have to combine them. So if it doesn't, let's say all four of these were different, right? All four were different factors. You'd have a huge common denominator. It would be 4 binomials multiplying each other. Right? If these all four were different, you have to multiply all four, which is a mess. So there's a good chance that you're going to have some sort of thing in common. Or maybe you have something where you have like, imagine this denominator here, right? Look at this denominator right here real quick. Imagine this had been instead something like this, x squared minus 5x. Well, you'd have to factor out a x and remain with x minus 5. But you'd still have the x minus 5 in common between the two. Okay, so look for that for a GCF. A lot of the time in these tests, they'll put a GCF and a lot of students will get, flustered. Take out the GCF first and you might have a common denominator already. Okay, but that's not the case here, so let's erase that. All right, now, if we have those denominator parts in common, what do we do to the numerators? What happens over here? Yeah, we first see some cancellation, right? This x plus 1 cancels. But before I cancel that x plus 1, let's make a common denominator real quick. So if I want to make a common denominator, what am I missing on the left fraction? What's missing on the left fraction that's on the right fraction? X plus 1. Well, actually, no, let's cancel it out first. I apologize. Mike's right. You know why? Because we're going to put x plus 1 in both spots. Then we're going to have to cancel it afterwards. So let's cancel these. Put a 1 here now. And then we'll just say, instead, Mike, good point. We'll just say that, you know what? Let's look to see what's missing on the right-hand side only now. It's simply just 1. Yeah, just the x plus 3. So that'll give us an expression down below. In the numerator, we have x plus 4 here, minus x plus 3, all over x minus 5, x plus 3. What should I do with the numerator? What does the numerator become? X minus x, what happens there? X minus x? 0 cancels. 4 minus 3 gives me simply 1. Okay? Again, notice up here that you have a minus sign up here. You're subtracting the whole thing. So 4 minus 3, x minus x. We did an example from 5-7. That was the one Mike asked about the problem set with complex fractions. You should be able to simplify complex fractions. Word problem type, because I know that was going to rain about a minute or two. How did you do on the 5-7 problem set word problems? How did you find them? Okay? I'm getting like shrugs. I don't know if that's good or bad.
It's a little weird to understand how to write it out, but then I figured it out.
Yeah, I think there was one that I didn't get. It was like,
So, do me a favor, Charles. Tonight, do the word problems first for 5-7. Email me them when you're done, so I can post the solution. Okay? So I'll post the solution to the problem set tonight for sure. He's just got to finish up his stuff, so that's good that I know that. Okay? All right. So since everybody else turned it in, I'll just once I get his, I'll post that up there. You might be ready for baseball, so it might be like 6 o'clock. Okay, but if you get it done early in the day, just let me know. You could expect, as far as expectations go, definitely be able to do a mixing problem. I'm going to give you one of those and tell you right now. The chemistry one, mixing problem, with the acid solution. Okay, it's a template problem. It really is a template problem. So all you have to do is practice. Take the example we did in class, change the numbers around. Okay? Maybe look at the other example type that they gave you in the book. There was another mixing problem where X was a little bit different at the spot. Look at that as an example. I'll put the solution out of both sides of these things when we work problems. Right.
Oh yeah, when you were going to read the test.
I'll probably give you 2. one mixing and then one, we'll see. The other one will be like a, yeah, I'll probably give you 3, choose 2. But the other one will probably be like a distance rate or, what was the other one we did? One of the examples, did you do one with interest, right? With interest rates for the problem set? Okay, some with interest rate maybe I'll give you. Okay, so anything from the problem set types. So definitely look at those solutions if you struggle with that.
Are you gonna have one that was like 20%, 60% of the number is?
That would be like the short answer in the middle of the test, yes.
Okay.
Okay, like, remember the problem is 20% of, 60% of. You do 20 over 100 times 60 over 100 times x equals that number. Look at the solution for that. Was that also 5, 7, Nina?
Yes.
Okay.